Finally, after all this work, we are ready to see the RSA crypto system. The RSA crypto system is a brilliant way of encrypting and decrypting stuff. It's something called a public key cryptography, and I'll explain what that means. The setup is the same we talked earlier, that you have Alice and Bob. Alice wants to send Bob a message, but there's a big brother in the middle who can listen to everything that Alice is saying. And so she needs to encrypt her message somehow. So Alice has a function. That function takes in two inputs, a message and a key, and it produces a cipher. And then Bob has another function, and it takes in the cipher and the key and produces the message. So decode and encode are almost inverse functions, but they have keys, they have an extra input in there. Now let's talk about what is known to everyone and what is secret. So as I mentioned, the functions encode and decode are usually known to everyone because you can only there are only so many protocols that people use. Of course, if you are doing something very top secret, then maybe even encode and decode are private. But for day-to-day communication, like when you're listening to this video on YouTube, YouTube is sending the encrypted packages to your computer, and it's not using some very secretive protocol. It's using some protocol that everybody knows. So these are public. Then the message is, of course, private. It better be private, like that's the whole point. The cipher is known to everyone. So you cannot trust any communication channel. You have to assume that there is an eavesdropper. And so the cipher is known to everyone. And that leaves us with the two keys. Okay, now in the first crypto systems you learn, or the first ones that existed, both the keys needed to be private. So we would have something like that. Okay, for example, in the Caesar cipher, key was the number of shifts you had to make. So Alice would shift by 3, and then Bob would shift back by 3. But if the eavesdropper knew the number 3, then they could shift it back by 3 themselves, and the message would be out in the public. So in Caesar cipher, both key A and key B need to be private. But this brings us to a meta question, which is then how would Alice communicate her key to Bob? Like in the Caesar cipher, Bob needs to know how much Alice is shifting to the right by. And so Alice, before she can communicate the message to Bob, needs to communicate the key to Bob. As soon as key A becomes private, communication is no longer practical between strangers. And so key A needs to be public. It has to be, otherwise a system cannot exist that can be used globally. And so this is the question. Is it possible to design a crypto system such that Alice, who is the encoder, has a key that is just known to everyone, and yet the eavesdropper cannot figure out what Bob's key is using Alice's key? So this is the question. Make it impossible to find Bob's key using Alice's key. And when I say impossible, I just mean impractical. And so the question is, can you design such a system? And the answer is yes. And that is the genius of RSA. And their idea is surprisingly simple. What they use is a very simple fact, let's say in computer science, that some mathematical operations are easier to do one way and harder to do the other way. That is, they use the fact that for some functions, f is easier to compute than f inverse. Of course, I don't mean this literally. I'm being a little vague here. And using this very simple thing, you can create RSA. And an example of this is that products are easy to compute. Prime factorizations are hard. there's no algorithms, and we don't expect there to be any simple algorithms that can do prime factorizations. So if you can have an encoding system that multiplies things and a decoding system that requires factorizations in some smart way, or rather if an eavesdropper were to somehow try to decode, they would need to do a prime factorization, but Bob may already know the prime factorization beforehand, so he can just decode, but an eavesdropper will not be able to decode. So that's the principle behind public key cryptography. Oh, and this is called public key cryptography because Alice's key is public. Everybody knows what the encoder's key is. But of course, the decoder's key still remains private. Okay, so now let's go into the details of RSA. Before we jump into the encryption, decryption, we need to do a little bit of a fair bit of setup. Okay, so the first thing Bob needs to create key A. That is, Bob needs to create the public key and just tell it to everyone, including Alice. Okay, so this is how he does it. He first picks two prime numbers, P and Q. Then he picks, and then he computes their product. And he computes one more thing, which is a little bit mysterious, but I'll explain this later. He computes P minus 1 times Q minus 1. Then he computes, or rather he picks a key, which is any number relatively prime. What I mean by that is any number such that GCD of key A and phi is 1. So this is the setup, and then Bob tells everyone the number n and key A. These two become public. And why n? Just so that the message needs to be any number. Okay, so Alice is going to somehow take any message she has and break it into pieces and convert it into numbers so that the message is now a number in Z mod n. But there is a second part that Bob needs to do, and this uses Euclid's algorithm that we have seen before. The second part Bob does, and this one is completely private. This is not known to anyone. Also, by the way, the primes P and Q are private. Similarly, phi is private. Whereas the number n is known to everyone, but not the factorization of n. This is what I said earlier, that it's easy to multiply, but it's hard to factor. So everyone knows what n is. It's just that they're not able to find P and Q from n. And then part 2 is completely private. This is only known to Bob. And what Bob does in the second part is he finds the multiplicative inverse of key A in, and here's a little different, it's Z mod phi. Okay, so he finds key B to be key A inverse in Z mod phi. So that's his private key, and this is only known to him. So that's the whole setup. So let me just summarize this. What is known to everyone, and then what is known only to Bob. So everyone knows N, and everyone knows key A. And then Bob knows the P, the Q, the phi, and the key. Okay, then the encoder is really simple. The encoder takes a message, which is, remember, a number in Z mod n, and of course the key A, which is known to everyone, and produces message to the key A mod n. And the decoder takes the cipher EV and produces and the theorem, you can show this using a little bit more modular arithmetic, that cipher to the key B is the original message. That is, this is the theorem that makes the RSA system work, but it's the proof of this theorem is beyond the scope of our course. Let's see this in action. First, Bob needs to do the setup to generate the private key and the public key, and so he needs to start with picking up 2 primes. For the sake of simplicity, we'll take very small primes, but in practice, these primes are hundreds of digits long. So these are the primes. Then the next step is to pick n, which is to compute n, which is p times q, that is 3 times 5, that is 15. And then we compute phi, which is p minus 1 times q minus 1, and that is 3 minus 1 times 4 minus 1, which is 2 times 5 minus 1, which is 2 times 4, which is 8. Bob needs to come up with the key A, and key A can be any number such that GCD of 8 with key A is 1. So Bob has to make a choice. There are many possible numbers which are relatively prime to 8. And so let's just say pick 7. Which of this information is public and which is private? The n is a public information, or rather just 15 is the public information, and then key A is public. So he tells this to everyone. Everything else, the P, the Q, and the phi, these are private. These are not known to other people. Okay, so that's the first part. Now for the second part, Bob needs to find key B, which is key A inverse mod phi, which is 7 inverse mod 8. And now in a standard problem, you would solve this by using Euclid's algorithm. But I'm going to do a trick here because 8 and 7 are small numbers. So here 7 is nothing but minus 1 mod 8, because 7 is 8 minus 1. But minus 1 inverse is just minus 1. And then minus 1 is 7. Okay, so in fact, turns out that key B is again 7. Okay, so with that, let's summarize what we have. So we have in public, everyone knows that n is 15, and everyone knows that key A is 7, and only Bob knows that key B is also 7. All right, now let's encode. So now suppose Alice wants to send a message. And again, for simplicity, I'll pick the simplest possible message. Suppose she wants to send to mod 15. Remember that Alice sends a number mod n, in this case 15. So suppose her message is to mod 15. So how will she send it? She'll use the encode function. The cipher will be encode the message and key A, which is nothing but message to the key A mod n, which in our case is 2 to the 7 mod 15. And I'll use the fast exponentiation method to find this. So this is 7 we saw is 4 plus 2 plus 1. Or 7 is binary representation, gives you 4 plus 2 plus 1. That is 2 to the 4 times 2 squared times 2 mod 15. And 2 to the 4 is 16 times 4 times 2 mod 15. And that gives me 16 is congruent to 1. 16 leaves the remainder 1 when divided by 15. 4 leaves 4 and 2 leaves 2. And so that's 8. So that is the cipher that Alice sends to Bob. And note that this cipher is public. So everyone knows that she's sending 8. What what is private is this number 2. So it's not 8 that is the message, it is the number 2 that is the message. So you can think 2 may be the password to something. And now Bob needs to decode this. And how will Bob decode it? Bob will say that the message is, take the cipher and key B and raise the cipher to key B mod n, and that is 8 to the 7 mod 15. 8 is 2 cubed, so this is 2 cubed to the 7, and then that is 2 to the 21 mod 15. And let's see if we can figure this out. 21 in binary is 21 is 16 plus 5, that is 16 plus 4 plus 1, that is 2 to the 16 times 2 to the 4 times 2 to the 1 mod 15, and 2 to the 4 is 16. Oh, I see a trick here. I can write 2 to the 16 as 2 to the 4 whole to the 4 times 2 to the 4 times 2 to the 1. Now 2 to the 4 is 16, so I get 16 to the 4 times 16 times 2 mod 15. And 16 leaves the remainder 1, so 1 to the 4 times 1 times 2 mod 15, and that is the message that Bob finds after using RSA. Let me just quickly show you the whole thing again. This was the public key. Everyone knew this. This was private, only Bob knew this. Then Alice had a private message which was 2 mod 15 that she wanted to communicate to Bob. So she uses the encoding function message to the power of key and produces the cipher 8, and she sends the cipher 8 to Bob, and this is public. Everyone can see the number 8. What they cannot see is where it came from. And then Bob uses the decoding process, which is you do the same thing. You raise cipher to key B mod n, in this case 15, and he finds that the message that Alice wants to send was 2. Okay, so now let me quickly explain or summarize why RSA is hard to break, for 2 reasons. One, it is hard to factorize n. So everybody can see the capital N, but still from that capital N, they can't find what P and Q are. And of course, if you choose bad primes P and Q, then someone can write a smart program that can actually factorize it. So you have to be smart about your choices of primes. And secondly, given message to key A mod n, it is hard to find. Oh, and key A. So remember that the cipher is known to everyone because we cannot assume that any channel is secure. So this is completely known to everyone. Similarly, the public key is known to everyone. But even if I know message to the key A and key A, it is hard to find message mod n. Okay, that is, it is hard to find what was the number whose key eighth power is the cipher. Now, when I say it is hard, I just mean that we don't have any algorithms so far, and we don't expect to find good algorithms anytime in the near future. This has something to do with the P versus NP question, or even stronger. I'm not entirely sure. But that doesn't mean that this can never be broken. In fact, if quantum computers ever came into existence, then there exist quantum algorithms that can factorize much faster. But in that case, we can just replace multiplication and factorization processes by even more complicated mathematical processes, which are harder to break even for quantum computers. So that's how the different crypto systems differ. They use, instead of multiplication and factorization, they'll use a more complicated function and its inverse. And so you can create harder and harder and harder crypto systems. And that is all there is to RSA.